Alright, we're going to talk about enthalpy, enthalpy change, and enthalpy diagrams. And believe it or not, we don't really care too much about enthalpy itself. It's actually the enthalpy change that is more of interest. So enthalpy, to sum it up, is kind of like all of the heat content that is found inside of a system. So you can kind of think of it like the ability or the potential amount of heat that it can transfer to something else. And it's very hard to measure that, which is why we actually shift our focuses to measuring this right here, our delta H. Earlier we had talked about how to write thermochemical equations. So for example, if you had something like this, you had calcium oxide solid reacts with water, and that'll produce calcium hydroxide. Right, so that's just a regular chemical equation. It turns out that to go from these reactants to this product, there is a change in enthalpy. Bonds are broken, bonds are formed, and those are energy differences, and we calculate delta H from that. So if we were to write the two different thermochemical equations for it, we can write this one where it's actually a reactant or product, or we can write the chemical equation and afterward write delta H is equal to. So remember, if we're doing it this way, if it appears on the product side, what that tells us that it's being produced, that tells us this is exothermic. So the second way to write it, what tells us that this is exothermic is that negative sign. So this delta H is called the heat of reaction. Reactions shortened RXN. So it's the amount of heat, it's the heat difference that occurs when this specific equation or reaction takes place. So you could actually go ahead and write the heat of reaction for any reaction. So for example, just by looking at this reaction, the combustion of methane, right, or specifically 1 mole of methane, has a heat of reaction equal to negative 890 kilojoules. All physical and chemical processes involve a change in enthalpy. So let's consider this scenario here. This is a physical change. We have solid water, 1 mole of solid water converting to 1 mole of liquid water. So assume we had 1 mole-ish, right? It's going to involve some kind of heat change in order to turn into liquid. Question is, does it need to gain energy or lose energy? Well, if we think about it like particles, right? In the solid, the atoms or the molecules are in fixed positions. So in order for them to behave like liquid, right, they're kind of close to each other, but they're actually able to slide past each other, right? They have intermolecular forces. Do you think they would need to gain energy or lose energy? Well, think of it like this. You have to invest heat or energy into the system so that they can move faster. So this is going to be an example of an endothermic process because they are absorbing energy so that they can move faster, which means that this is going to absorb a certain amount of energy, right? So that means that our delta H for this scenario is going to be positive, and more specifically it's going to be 6.01 kilojoules for every 1 mole. Okay, but what if it was different? What if we had the reverse? What if we had liquid turning into solid, right? What would delta H be? Assuming you had 1 mole of H2O liquid converting to 1 mole of H2O solid, do you think, given the previous information, you could figure out what the value for delta H would be. Well, if you're considering the law of conservation of energy, then you know, or should know, that if it took 6.01 kilojoules per mole to go from solid to liquid, well then to do the reverse, right, if we look at from liquid to solid, these particles are sliding past each other, moving around. In order for them to go into a fixed position, to no longer be moving, they have to have less energy. Therefore, they have to lose energy. Specifically, 6.01 kilojoules per mole. So the delta H for 1 mole of liquid water freezing into 1 mole of solid is going to be negative 6.016 kilojoules per mole, which happens to be an exothermic process, right? Remember, when it's negative, it's exo. When delta H is positive, it is endo. All right, let's get graphical. So, the most common way that, another visual way to see delta H, right, or change in enthalpy, is to have an enthalpy diagram. So typically, an enthalpy diagram looks something like this, and your y-axis is enthalpy, right, so it's increasing as we go up. And remember, enthalpy is the heat content, the potential amount of heat, right, that can be transferred in a system. So in a reaction, the reactants, they have a certain enthalpy. The products, they have another enthalpy value, right? So depending on whose is higher or whose is lower, that tells you this is going to be an endothermic or exothermic process. So let's go back to that calcium oxide and water reaction. So if we had calcium oxide, which is a solid, and it's reacting with water, which is a liquid, it turns out that the enthalpy value, actually let me draw a little line here, right? So this is representing your reactants. It turns out that the enthalpy value of the products is much lower than the enthalpy value of calcium oxide and water. The enthalpy value of calcium hydroxide is down here. And so, like I had mentioned before, it's very difficult to measure the enthalpy of a system, right? But it's much easier to measure the enthalpy change in a system. So in this case, we have our reactants up there and our product down here. What that means is when this reaction takes place, the overall system is going to go from a higher state of enthalpy to a lower state of enthalpy. So this distance right here, that is your enthalpy change, your change in enthalpy. And because you're taking a lower value and you're subtracting a larger number from it, you're going to get a negative value. And in this case, it turns out, I think we mentioned it earlier, negative 65.2 kilojoules. That is the enthalpy change for this reaction. Now, if it were the reverse, right? In this case, we're going from CaO plus H2O to CaOH2. If we were to go the other way, if we were to go from CaOH2 to CaO plus H2O, right? Well, in that case, our delta H would be positive because we have to gain energy to go from CaOH2 all the way to CaO plus H2O. And if you should be able to predict what the value for delta H would be, positive 62.5 kilojoules. So, reminder, if your reactants are up here and your products are down here, going downward this way, your delta H is going to be negative, and this is an example of an exothermic process. If your products were up here and your reactants were down here and you're going this way, well, that height difference, right, means your delta H is going to be positive, and this is going to be an endothermic process. That's always the case. Going down, exo. Going up, endo. Alright, so now let's go ahead and throw it all together. So let's go ahead and make another energy diagram. Right, where going up is increasing. And let's consider the three states of matter: solid, liquid, and gas. So between those three, which state probably has the most potential to release heat? Well, you have to think about it. Whose particles are moving the fastest or the most? So solids, remember, they are in fixed position, the particles. Not a lot of energy, right? So this is typically considered low enthalpy. If you consider liquids, so the particles are still close to each other, right, but they're able to slide past each other. More kinetic energies than the solid, more enthalpy than the solids. And then we have the gases, right? So I don't know, how do you want to draw the gases? That was horrible. Maybe something like this. That's super bad. All right, but the idea is that these particles are traveling, right, super fast in multiple directions. All right, so we know that going from a lower state to a higher state involves absorbing energy, so the particles can move faster. And going downward, slowing down the particles, is releasing energy. So we're going to include some terminology here. So let me go ahead and label them. Here we have solid, we have liquid, and we have gas. Alright, so anytime any solid is going to go to liquid, right, it's going to absorb energy. Therefore, that tells you that your delta H is going to be positive. That's gross. Now let's try, I'll just do it on the other side. Alright, so our delta H, that's not going to work. Now let's try, these are like, yeah, this guy's taking forever. Here we go. Delta H is positive. Okay. To go from liquid to gas, it requires absorbing a lot more energy, because now these particles have to be traveling fast enough to escape any intermolecular forces. So usually there's a greater amount of energy that needs to be absorbed for a liquid to go to a gas than its solid component turning into liquid. So delta H is still going to be positive in this case, but significantly larger. So we know that melting and vaporization is an endothermic process. But remember, there's also another process going upward. I'll pretend to give you time to think of what it is. Going from solid all the way to gas. So that is called, very good, sublimation, which also has a positive value for delta H, which means it's also an endothermic process. And it also happens to be the sum of these two enthalpy changes right here. And it just so happens that the reverse processes, going from gas to liquid, condensing, right, that is going to be an exothermic process. These particles, as they start to slow down, it means they're going to give up energy. So your delta H for that is going to be negative. And to go from liquid to solid, it has to slow down even more, which is going to result in, again, another loss of energy or enthalpy. But there's another one, going from gas all the way to solid. This is also going to be an exothermic process, so your delta H is going to be negative. And also the sum of the delta H of those two previous processes. Alright, so some terminology that you need to know. We'll pick them apart one at a time. So let's do the easy ones first. If you looked in your definitions, you saw this: molar heat of, and then it was like something. And you had like several of them, like 6 or 7 of them. So I'm going to go ahead and explain them right now. The molar heat of anything is the amount of heat exchanged for every 1 mole of that substance. So for example, you have molar heat of combustion, which is the energy exchanged to combust 1 mole of a substance. You have molar heat of vaporization, the amount of heat required to vaporize 1 mole of a liquid sample. So the term melting has a more technical term, more scientific term, and that term is fusion. So the enthalpy change involved when 1 mole of a substance melts is represented like this: delta H FUS, which is molar heat of fusion, which is the amount of energy it takes to melt 1 mole of a substance. Freezing also has changed. It also has a more technical name. You know it as freezing, but moving forward, we refer to it as the obvious solidification. So if you had 1 mole of a liquid and you were to freeze it and calculate that delta H, it would be represented by delta H SOLID. It's the amount of energy required, right, to freeze 1 mole of a substance. Now, what is interesting here is that the sign is going to be negative because this is an exothermic process, right? Going downward, going from liquid to solid is losing energy. Going from solid to liquid is gaining energy. So this one is endothermic and this one is, this one is exothermic and this one is endothermic. And when you're talking about the same substance, it turns out that its molar heat of fusion, that magnitude is going to be the same as its molar heat of solidification. The only difference is that one of them is going to have a negative sign. The other phase changes, they don't change. So going from liquid to gas, that's called vaporization. So the molar heat of vaporization, right, is some amount of kilojoules required to vaporize 1 mole of a substance. And the opposite process, condensation, well, the molar heat of condensation is equal to negative some amount kilojoules per mole. And yes, it turns out that they are equal to each other. The only difference is one of them is negative. And finally you have solid, going into gas. That's sublimation, so you'll write the molar heat of sublimation is some amount of energy required for 1 mole of a solid to sublime to gas. Molar heat of deposition is equal to the negative amount of kilojoules required for 1 mole of a gas to deposit into solid. Again, the molar heat of sublimation for the same substance is going to be the same value of the molar heat of deposition of the substance, just opposite in sign. So a refresher: solid turning into liquid, liquid turning into solid, solid turning into gas. These are always going to be endothermic processes. Delta H will always be positive for these processes. Going from gas to liquid, liquid to solid, gas to solid, these will always be exothermic processes. Delta H will always be negative. They will always release energy. Whereas endothermic processes, right, they are absorbing energy. The particles speed up because they gain the energy in an endothermic process. The particles slow down in an exothermic process because they lose energy. The last molar heat we're going to talk about is the molar heat of solution. So solution like that. So the idea there is, if you had a container, let's just say we had a beaker, and this beaker has a certain amount of water. If you were to take, for example, sodium chloride, 1 mole of sodium chloride, and you were to put it in water, well, we know that the ions would break up. Well, this is a physical process, right? The ions are separating. That means there's a change in enthalpy. So it turns out that the molar heat of solution of sodium chloride is an endothermic process. What that means is there is an investment of energy going into the system. That's actually misleading. It's probably coming from the water. There's the reaction of the sodium chloride ions and the water molecules are absorbing energy. So if we had a thermometer that was extremely sensitive, we would note that the temperature change, it would have a decrease in temperature. So we know that I don't want to say a temperature change. That can be misleading. So the temperature would go down. It would get colder because it's pulling in energy. Unfortunately, we can't say that all solutions, all things dissolved in water are endothermic processes, because if we took something like calcium chloride and try to dissolve that in water, that would break up into the calcium ions and the chloride ions. Turns out that the molar heat of solution for calcium chloride is an exothermic process, where the molar heat of solution for sodium chloride is positive. So you can't predict necessarily what the sign of an ionic compound is going to have when it dissolves in water.